All right. So thank you so much for joining us on Wednesday, and thank you so much for taking the time to take the opportunity to discuss something the AEC industry cares a lot. So today we're going to talk about building energy conservation codes and energy modeling. I believe in the design engineers and for PMs, for consulting engineers, we deal with energy conservation codes all the time, and sometimes we, energy modeling is probably not as common as you deal with energy conservation codes, but still we use it very often. So today, let's just talk about some details. All right, so our agenda today, we're going to talk about energy conservation codes. Obviously, there are lots of stuff there, and there are different types of energy conservation codes, and there are different scopes and different content. And we're going to talk about energy modeling. A lot of people, heard about it, and a lot of people use it, and a lot of, actually, I saw a lot of energy modelers here. We're going to talk about, how we use energy modeling, in different scenarios, how we apply energy modeling in different types of projects. And I also want to take a step further. Just to show you how to do an energy model. We always talk about it, but I think a lot of people never actually see an energy model. Some of the details, what's in there. All right. So I would like to start this section with two discussion questions. During this difficult time of COVID-19, we probably, most of us are just staying at home right now. And we often ask us, what is the main purpose of the buildings? So you guys can, send, your answer, your thoughts on, through the chat. We can see them. So I guess, you guys are right. Buildings are built to protect us from weather and to create comfortable and healthy thermal environment. Actually, healthy was not there in the definition. We oftentimes just, think it's a shelter. But probably a lot of people in the AEC industry right now are thinking, rethinking this. Probably, healthy is gonna get more popular in the future. We want a very comfortable environment, but we also want a healthy building. And we spend lots of time, majority of our time inside. And the second question is, I saw a lot of PMs here, project managers here. You guys probably know this much better than we do. So the second question is, can you build whatever the way you like? Like I want to build something like a, like window ratio like this one building here at 80 or 90%. Can we build whatever the way we like? You guys can send the answers or your thoughts through the chat. Can we build something like this in Chicago? All right, possible. Yep. Anyone else? All right. Yes, we can. Yes, we can. We can. So architects probably not gonna pass com checks, but we can. It's as long as you provide documentation proof, it's more efficient and it complies with mandatory regulations. And here by, I saw one answer, anything is possible with time and money. Yes, that's true. This building, if in a cold climate zone, it's going to be very expensive. Even in a warm climate zone, it's going to be very expensive. You're going to, it's very good looking, but at the same time, you're probably going to spend so much money on lighting and HVAC. So you have a better performance than the code. All right, let's start the energy conservation code section. So in the US, there are several types of energy codes, and there is no federal level energy code. So the most three common ones here, and we have a lot of designers here. So we deal with IECC and ASHRAE. IECC is International Energy Conservation Code, and ASHRAE is from ASHRAE. They use 90.1, and they have 90.2 for residential. So those two are the most common energy codes we see in the US, and most of the states, they adopt different version of them. And oftentimes, the counties, the state, they have amendments. Like state of Washington, they adopt IECC, but they just modify so much. They pretty much rewrote a lot of sections of IECC, and it make it so stringent. But it's still based on IECC, and IECC is actually very similar to ASHRAE 90.1, and it was based on 90.1. You're gonna find very similar writing and very similar requirements, the same efficiency requirement, pretty much very, very similar. So generally IECC is a little bit, ASHRAE is a little bit more stringent. IECC is, most of the times designers go with IECC. And there is one very unique state in the US, that is California. California has its own energy code. We call that Title 24. I'm not really sure if we have California people here, but if you ever work on California projects, you definitely know Title 24 is very different from IECC or ASHRAE. So it's designed to be a little bit more stringent than ASHRAE. Some of the, if you, let's say if you practice in Illinois and suddenly you have a project in California, you have to pay attention to the energy code, because some of the common practice you do in other states are not necessarily what they do in California. And sometimes, it really surprises you. All right, I want to take a step further and go into the energy code and see what's in there. So first, the scope. Basically, and the purpose of energy code is to save energy, right? They regulate the way you build, the equipment you buy, the equipment you install. So basically, so who has to comply with energy code? Basically, if you build a building and you have to apply for a building permit, most likely, yes, you have to comply, and it's mandatory. Even there is no federal level, but from the state level or county level, in the US, if you have to have a building permit, then most likely you have to comply. And as we see here, it's mandatory on new buildings, additions and alterations to existing buildings. That means major renovation. You have to meet the energy code requirements, and in order to receive a building permit. Here, manufactured mobile and modular homes and unconditioned buildings are not covered. So they're not regulated by this energy code. And in the energy code, as you can see here, I screenshot this chapter, so we have building envelope that, architects cares about building envelopes. We work on energy models and on energy code all the time, and we oftentimes get the most common question from architects are, can we, the insulation level, R20, R30, like air barrier question, like roof membrane question, all those stuff are regulated in the building envelope section. And we oftentimes, there's also HVAC section. Basically, it regulates the efficiency of the equipment. Let's say if you have a heat pump and the code is gonna regulate the efficiency of the heat pump. Let's say for cooling, you have to have a minimum EER of 10. For heating, you have to have a minimum COP of 3, things like that. So you cannot go lower than that. That's why it's, it regulates. And also, well, it doesn't really have a lot of stuff for plumbing engineer. The most related stuff here is a service water heating. Basically, if you have service hot water in the building, and if you have water heater in the building, you have to comply with the minimum efficiency requirement. And also there's the power and lighting part for the electrical engineer. I know a lot of electrical engineers are not happy about it. The ASHRAE shouldn't write too much about lighting. But lighting is there, and ASHRAE actually regulates a lot of stuff about lighting. The lighting power density you have, and the controls you need to have, what kind of daylighting controls, what kind of step controls or dimming controls, shut off controls, things like those. It's regulated in ASHRAE. And also there's power and some other equipment, also related to electrical engineer. ASHRAE doesn't really say too much about those. Some of the there's some of the stuff are not regulated, but oftentimes we do not deal with those. Well, sometimes we do. All right, so I guess this is the part where most of the design engineers, designers, architects, MEP engineers care about. The question is how to comply. We have an energy code. We have to comply, right? But how? And I believe most of the designers, they use ComChecks. It's a great tool. It basically put the information of your proposed design into the tool, and you run a report. Then it tells you if you comply or not. So generally, so let's start from IECC. I'm not going to talk, the details about Title 24. The content is a little bit different, but the idea behind the compliance path and the principles are pretty much very, very similar. So you can just use this as a reference for Title 24 as well. I'm using IECC as an example here. So if we're using IECC, and in IECC it says, you can use ASHRAE. So basically those two are equivalent. You can use either ASHRAE or either IECC. You cannot use, for say in this project, we use this part, we use 90.1 and that part we use IECC. No, you cannot do that. You have to pick one. So let's say we use IECC. In IECC, there are different sections, and there are different types of requirements and regulations. So there are mandatory parts, and there are prescriptive parts. So mandatory, I think a lot of people are confused. We often got asked questions like, do I have to comply this mandatory, provision if we do a performance base? The answer is yes. If you go into the energy code, go to the energy code and you read it, sometimes there is mandatory next to to the section, and there is prescriptive next to the section. Mandatory means what compliance path you choose, either energy model or either prescriptive, you have to comply with mandatory requirements. After you comply with mandatory requirements, then you can choose, if you want to go step by step, that is prescriptively, or you want to go for a whole building performance, compliance path. That's an energy model. And if you do prescriptively, like I mentioned, that's probably the option most designers are familiar with, because they can use com checks. And also I put a limited trade-off option here that is also available in com check. Let's say the code baseline says I have to have R30 roof and R10 exterior wall. But in my design, I have R20 wall and R25 roof. Do I comply? You can do limited trade-off in com check and see if you comply or not. All right, I got a question here. Envelope trade-off require energy model. Can that be? No, you don't need an engine model. So this envelope trade-off option is you can do that through com checks. You don't have to do an engine model. You can do, so if you run com checks, you can see a com check give you a report, say my proposed overall envelope is how much better than the code. That is kind of like a trade-off idea. So you don't have to run an engine model. Engine model is a whole building. You also consider the HVAC, the lighting, the plumbing part. But here, the limited trade-off is just within the envelope. All right, but that's not the part we're gonna focus. We're not gonna focus on prescriptive because, I believe you guys are as designers, you guys are very familiar with that part. And today we're gonna focus on the energy model part. How do we comply through performance method? So first, no matter what, first thing first, you have to comply with mandatory requirements. You have to have air barrier. You have to have, sometimes economizer. You have to have energy recovery. Sometimes, well, you have exceptions, but some, lots of stuff are mandatory regulated. You have to have those. And then we use engine model for compliance. So the idea of using we call that performance, is, the building is not, we don't evaluate this building just based on its HVAC. We don't just evaluate this building based on its electrical system. I mean, it's a whole lot of stuff, a bunch of stuff in one box, right? So the idea is we look at the building as a whole system. We evaluate the whole building. With that being said, if you have a great envelope, let's say I have like R30 wall, I have R50 roof. Does that mean your building is really efficient? Is that high performance? No, not really. Oftentimes, probably that's not the case. If you have a crappy HVAC, you have a crappy electrical system, your buildings, even you have great envelope, but it's probably not going to perform well. So we can go into details in the next section. So if you do an energy model for compliance, there are two different types. There are energy based or EUI based. That is, I put an example here. So my proposed design has an EUI of 50 and the code baseline is 60 and my design complies. So that's the case in Washington, state of Washington, state of New Jersey, and state of California. So basically, they don't care about how much money you spend on the utility. They don't care about how much money you spend on electricity, on natural gas. They care about how much energy you consume. And for most of the states, actually, it's based on cost. That means, let's say my proposed design has a total utility cost, electricity plus natural gas, $10,000, and my code baseline is $15,000. My design complies. And in this case, your EUI, your proposed design EUI, is not necessarily lower than your baseline. So that's for most of the states. And be careful here because that's a huge difference. And if it's energy-based, it favors electrical type of design. Basically, if you have heat pumps, even you have electric resistance heating, and you have heat pumps, it helps with the design. But if it's cost-based, it favors fossil fuel, it favors natural gas, because natural gas is really, really cheap compared to electricity. So you have to have overall like COP of 3 to beat natural gas if you are using electricity. So I would say most of the states right now under the compliance, under their energy code right now, they favor fossil fuel type of design. And a lot of people don't agree with that, but yeah, that's what it is right now. So and as I mentioned, so there's in the U.S. there's no energy code, like there's no federal level energy code. The federal government doesn't regulate what energy code you have to use. They don't have one. So each state adopts their own energy code, their own version of the energy code, and oftentimes they have modifications and amendments. Sometimes, like state of Washington, we just did several projects there. They made it. Their amendments made the energy code so stringent, and it's so hard to comply. And in the past 40 years, through ASHRAE 90.1, we see dramatic, savings, improvements from the energy model, from the energy code, sorry. So as you can see here, ASHRAE 90.1 2016 is pretty much 50% more efficient than 40 years ago. Well, I mean, that's a great progress. And I know there are some sustainability consultants here, and some PMs are here. So we often deal with certification programs like LEED, Green Globes, Energy Star, Green Enterprise, Green Communities. Pretty much those certification programs were developed based on energy code, for the energy section, for their energy credits. They were developed based on, they're referencing different version of energy code, different criteria of the energy code. Also, the utility companies, they also reference energy code. Basically, I believe a lot of people in the Chicago area are familiar with ComEd. So they offer new construction incentive, and the new construction incentive is based on, you compare your your building design to a baseline, then you prove how better you are, and then they give you incentive. Well, the reason why I put Connecticut is I am in Connecticut, and they offer some incentive program based on based on their state energy code. And also, I am using Chicago as an example here because I know probably most of you are from Chicago area. And the local government incentive, sometimes it's not really incentive program, but sustainability program. So like Chicago, they, in the development PD policy, so they have this Chicago Sustainability Development Policy. Basically, in the energy part, they're also referencing the energy code. So as you can see, in this industry, we have to deal with it. I mean, it's kind of like a fundamental stuff everyday stuff we have to deal with. All right, so that is the energy code section, and I want to move to the modeling section. I know I saw a lot of familiar names here. I know lots of you are very experienced modelers. So if you see something you don't agree with, don't roast me too hard. Modelers do things differently. So I would try my best to be straightforward. So what is an energy model? Basically, we have inputs and we have a tool, and under certain structure, we grab those inputs, we put those into a tool, then we have outputs. That's kind of like a software type of idea. So what kind of inputs we have? Let's say we have a building in Chicago. We have this building in Chicago. This is actually a real building in Chicago. We have a design in Chicago. We have, we know the weather, we know the location, and from the drawings, architecture, MEP drawings, we know the geometry, we know the envelope, we know the MEP system. And also oftentimes we have to know the sequence operation, not just the HVAC, but also the building, how they operate the building, basically. So you put all those stuff are inputs. And what is a structural tool? In the past, probably 20 years ago or 30 years ago, people still do modeling through coding. They program and they input commands. I actually learned energy modeling through coding when I was at school. And those commands also are regulated by certain ruling, oftentimes in the industry. I'm not saying academia, because academia do things differently. So in the industry, oftentimes the structure, like how you do, like you follow rules, right? Those rules are regulated by the energy code. And there are also some reference book, like handbook from ASHRAE and BIPSA, that regulates certain ways of doing energy models. And here I put some of the most commonly used energy modeling software we use. So we have IES, UQuest, Train Trace. Train Trace is a very, a lot of mechanical engineers use Train Trace for sizing. And we have Transys. Transys is I'll just be honest, I don't really see a lot of Transys in industry. I see a lot of, when I was at school, they used Transys for academia research and design builder. And we have another great, very popular modeling software, Open Studio. And we have Energy Plus. Energy Plus is kind of like the engine behind a lot of modeling software tools. And also Carrier developed their own modeling tool called HAP. I never use it, so I'm not going to say anything about it. So at Cyclone, we use IES. We have done like 400 something models through IES. And then we have outputs. So what do we care? What do we want through energy model? Oftentimes, we care about, we want to know the temperature distribution. Say we have office space, we control that to be 70 Fahrenheit for heating and 75 Fahrenheit for cooling. We want to know, was the system designed to meet the set point? so we can get that through energy modeling. So this is the first picture here is a energy distribution, is a temperature distribution profile. It's 8,760 hours a year. So also we sometimes care about, say I have a chiller. I want to know the chiller, like the load profile on the chiller, so I know how how it runs. You can also do that through energy modeling. There are, so for load profile. All right, I got a question. Actual energy modeling consumption. All right, great question. I got a question. So the question is, what is the difference, deviation percentage in terms of actual energy consumption and energy modeling? This is a great question. So can I leave this question to the end of this presentation? I know a lot of people are going to be very interested in this discussion. Mechanical engineers care about, let's go back to the modeling part. So lots of mechanical engineers care about the load, let's say a chiller. And I personally do not know, you probably can manually do that or do a spreadsheet to get a load profile. You can do like a Bing type of method, but to get like 8,760 hours, the load profile is kind of hard. So modeling is probably the most feasible and it's not too much time consuming way to get it. And also, obviously, we care about energy consumption. We care about cost. We can do cost analysis based on the consumption profile and based on the demand profile. So that is the concept. So I am going to talk about applications of energy modeling. Obviously, it can be used in a lot of cases. So first case, that is for the designers. We can use energy model to support our design, no matter architecture or MEP. We call that parametric study. So as you can see, the first case is for architects. We oftentimes in high-rise building, like you see in Chicago, oftentimes they have very high window ratio, but a lot of times, you're not really sure the performance of different window ratio. You're not sure about R20 versus R10. You're not really sure, if I have solar band 60 or if I have solar band 70, different glazing system. What's the difference in terms of performance? Energy modeling is a great tool to evaluate. And also I guess for mechanical engineers, there are just so many HVAC options right now available. And in the same building, you can design a lot of different types of HVAC system. But how do you evaluate a different let's say in a residential building, I want to use a water cooled VRF plus a DOS system, or I want to use a water to air heat pump plus DOS. What's the difference? So you can use energy model to evaluate that as well. And also, we can use modeling for lighting controls. This is a typical daylighting dimming control here. We call that daylighting harvesting. So basically, you evaluate the availability of daylight, and then you run a simulation and see how much actual electrical lighting output you can save. So you can also evaluate through energy modeling. The application number 2, as we mentioned, we use energy modeling for code compliance. That is a performance pass. We use energy modeling to get building permit. I guess probably like 40% of the projects we do, modeling project we do at Cyclone are code compliance projects. We help designers, so they don't have to use contracts. We help them to we help them using engine model to get a building permit. So, and also many of you are very familiar with certification program like LEED. You also can use energy model to achieve LEED certification. Well, I mean, for the energy credit. So the energy modeling option gives you the most points. And also application number 3 is to predict. What does that mean? So first, net zero projects is getting, net zero is getting more and more popular today. Everyone, you see designers talk about net zero projects all the time. But, how do you, so the idea behind net zero is, you have to predict the consumption of this building and you size your renewables, like your PV system. Let's say we predict this building to consume 200,000 kWh electricity, then you know how big your PV system is going to be, right? In certain location, let's say 200 kilowatt. But how do you predict? Are you going to run a spreadsheet, regression analysis, something like that? You probably don't want to do that. You probably want to use an engine model to predict. You want to use a very good engine model to predict. You don't want to screw up your the sizing of your PV system. Also, another application is, I believe many of you have done this in the past. So the DOE, government, is offering tax incentive if your commercial building is more efficient than their baseline. We call that 179D. And their baseline is actually way back there. I think it's still ASHRAE 90.127. It's way back there. And in Chicago, we already use ASHRAE 90.116, ICC 2018. So a lot of times it's really easy. All right, application number 4. This is the part that's the most difficult part. And this is the most complicated type of model we do. We call that calibrated model. As you can, the idea behind this is you have an existing building. You want to evaluate some of the, let's say you have a retrofit. I want to replace the chiller. I want to replace the boiler. I want to, add some insulation to the envelope. I want to replace some of the windows. But how do you evaluate the payback? How do you evaluate, from energy consumption, how much energy you're going to save and how much money you're going to save? It's kind of hard to do. You can do that in a spreadsheet, calculation. But it's kind of hard. So we call that calibrated model. Basically, you have, this is existing building, and you build a model to calibrate the condition. Basically, the operation of your, the sequence of operation of your model is pretty much what they do in the building. So you build a model for the existing condition. And you calibrate because, people do things differently. People operate building differently. People have different ways of doing things and people run things differently. People like different temperatures. People like different schedule. And people like use some space, differently. So it has to go through a calibrated calibration process. And that is really, really, really hard. And that's why typically this kind of model takes so much time and so much effort. And, you need so much experience to do it. All right, last part, I want to show you guys, we often talk about energy model, but we never, probably, most modelers are not willing to show their models unless it's a lead project you have to show. So I want to show you what's in a model and the general steps of how to do an energy model. So first, you have, like we discussed in the inputs and outputs, this slides here. And so we have location, weather, calendar, and baseline. Those screenshots are, what took them from our modeling software, IES. So I'm using IES as an example here. You probably have different, you have different, slightly different steps in other modeling software, but generally the process should be similar. So, we have location, we have weather, we have calendar, and we have a baseline. Baseline is, what kind of energy code they're referencing. I'm talking about industrial type of projects, not academia. Academia, oftentimes they don't have a baseline. So, let's say we have a project in Chicago, then we define, the design condition, in winter and in summer, and we define a calendar. Different type of calendar, they have different results. So you have to be really careful there. And then we use the information from the drawings. We have architecture and MEP drawings. We develop geometry. Pretty much this geometry should be very similar, very close to the architecture geometry. And if it's not, well, you can simplify sometimes, but I personally tend to build something very close. Because if you build something very close enough, the solar part gonna be more accurate. So, and you define envelopes, you have exterior walls, you have roof, and you have glazing system, you have shading, you have slab on grade, sometimes you have, edge cover. So all those kind of good stuff. And then the next step is we define, we build all those spaces, right? It's made up of, lots of spaces. We have to define, the characteristic of those space. Let's say we have office building. We have office space, it has people, it has lighting, it has receptacle. We have defined those, right? Let's say we have 20 people, we have 0.7 watts per square foot lighting, and we have 1 watts per square foot receptacle. We have to define those. And then we have to define a profile. Those, you're not gonna have 0.7 watts per square foot lighting all the time, 24/7. That's not the case. If that's the case, that's wrong. So you have to have a profile. Something like this, during the day, you turn most of the lights on, and when most people are gone, you just turn them off. So, and we also have to implement lighting controls. Let's say we have auto shut off control, we have daylighting control, also receptacle controls. And the next step is, there are lots of stuff happening in a building, right? You have, if it's a high-rise building, let's say a 40-story building, you're gonna have lots of elevators, and you're gonna have huge elevators. You're probably looking at like 200 kW per elevator. Oftentimes, they different types of elevator, traction, regenerative, just different drives. And those elevators, they actually consume a lot of electricity, a lot of energy. So you have to count them. And we have exterior lighting, and we have service hot water. And in Chicago, if you are in Canada or some very cold climate zone, most likely you probably have snow melt system. And service hot water is actually really important part in an energy model, especially for a residential type of building. I think oftentimes a lot of people don't really pay attention to service hot water modeling, but in residential, especially multifamily, high rise, in some cases, you probably have more energy consumed to generate hot water than heating. It's just people use so much hot water. And if you don't model them correctly, your EUI is gonna be way off. So after we define those, all those miscellaneous stuff, then we go to the HVAC. I think that's a part most of the modelers struggle. This is the most difficult part, I would say. Here you are not, you grab the information from the mechanical drawing, right? You have the, how big is your fan? Do you have a VFD on them? How big is your cooling coil? What type of cooling coil? How big is your heating coil? Do you have cooling towers? Do you have boilers? Do you have a chiller? Things like that. But actually, those are easy to input. I mean, if let's say I have a 40 brake horsepower fan, I mean, I just put 40 brake horsepower. But the difficult part is the control. So that's why you need, for most of the modelers, we need to understand the controls of the HVAC, basically the sequence of operation. You have to talk to the designers, see their intention and how the system is intended to operate. Do you turn, do you run the fan continuously? Do you turn them on and off? Do you cycle them? And what is the supply temperature of this cooling coil? Do you supply 55 and reset that to 60? Or do you just supply, constantly 55? Things like that. And what kind of, pump control in the, for your condenser loop, those things are very, lot of detailed inputs and a lot of thinking behind, behind this HVAC. And the last step is to simulate. So you build everything, you build geometry, you build envelope, you have the electrical system, you have all the miscellaneous stuff. You define the operation schedule, you define all the profiles, then you simulate. But oftentimes, you're not gonna get a perfect model, after one simulation. Oftentimes you have to go back and debug. You make mistakes, make a lot of mistakes, lots of mistakes. You have to go back and modify and change some of the inputs, some of the controls, some of the numbers, and then you have to analyze. Let's say my room is designed to be at 70 Fahrenheit for heating. Does my system work like that? You have to analyze. And after, then you have to report, right, for different purposes. If it's for permit, then you have to do permit documentation. If it's for lead, you have to do lead documentation. For different purpose, you have to do different types of documentation. All right. Yeah, I guess that's the last slide. And we're gonna go to the Q&A session. So first, I would like to show you this question I got. Sorry, it's privately, but I think it's okay to show you guys. It's a very, very, very good question. So what will be the deviation percentage in terms of actual energy consumption in engine modeling? Most modelers don't have experience in real building operation. I have a little bit. I have done some retro commissioning, so I will try my best to answer this question. I would say oftentimes a lot. The difference is a lot. Especially if the model is built, let's say just for permit purpose or lead purpose, the model can show very different consumption from the real operation. But if the model is built like a calibrated model, it should be very, very, very close. If it's not close, you probably didn't calibrate the model well. So I hope that answers your question. And I know a lot of modelers are here. You guys, I mean, you guys can feel free to, send your thoughts. So the question is, in your experience, what was the maximum savings you have seen in a building with respect to standard? I guess probably around like a 60% that was a lead project. So lead, they have different versions, and that project was a lead version 3 project. So the reference ASHRAE 90.1 2007, and it's way back there. 2007, they don't even have daylighting controls written in the code. So the building was a warehouse, actually. The building was a warehouse. And typically warehouse type of buildings, they save a lot. They perform much better than the code baseline. So yeah, 60% was the maximum savings I have seen. And that was a warehouse type of project. The main savings are from better, better envelope. They have well insulated external wall and roof. They have very well designed lighting system, all LEDs, and they have very direct gas fired makeup units, high 92% efficiency. So yeah, 60%, that is a lot. So they basically got all the energy points in LEAP version 3. All right, we're gonna move to the next question. How hard or easy it is to calculate exact energy consumption of HVAC equipment in multi-story building? Can we calculate ROI of VRV chiller cooling tower for the same building? Yes, you can. Yes, you can. That is why you can use a calibrated model, or you can use something like this. You definitely can. You definitely can. It's so to build a good model, you have to understand, the modeler has to understand the SOP of the HVAC equipment. Whatever shows on the drawing is not necessarily the same. People understand things differently. Like I said, if the set point of a cooling coil on the schedule is 55, some modeler is probably just going to put 55 there all the time. They don't even reset the supply temperature, and that's wrong in most cases. So you have to understand this SOP, and then you can build a very good model to. So basically, this picture here shows the sequence of operation, shows how you operate this HVAC equipment. I would say it's hard, but it's doable. It's definitely doable. We do that. Very often. We do that very often. Hope that answers your question. So I got another question. Is it possible to model a net zero building? If yes, which software you suggest? Definitely. I mean, modeling. To be honest, I think it's one of the greatest tools for net zero buildings. You can definitely use. You can definitely model a net zero building. But like I said, because you predict consumption gonna affect the sizing of your PV, so you have to be really careful when you do the model. You don't want to mess up the systems. You don't want to mess up the inputs. You definitely can do that. So typically you do a model in the design phase. And I guess you probably have to talk to the designers very, very often, because they, typically net zeros are not easy to achieve. Well, if it's in California, it's probably easier, but if it's in Chicago, in Chicago or in the East Coast, it's probably not that easy. So you have to be really careful. And you have to understand the designs very well. So I guess you probably have to deal with designers all the time and more often. And which software I suggest? There are a lot of softwares available. Cyclone, we use IES. I use equasts in the past. I used trances in the past. I even coded. I even did programming in the past. But I think, you know, I personally like IES. So if you want to try, I would. If you never have done modeling in the past, I would suggest you to go with equasts first. That's very so it's hands-on. And then if you want something more flexibility and complexity, you probably want to try trances and IES. Trances is also a great tool for net zero modeling. It can size the renewable system very well. And IES is a great tool as well. And also you can do Energy Plus, but Energy Plus it's very complicated. All right, hope that helps.
Alan?
Yes.
There's one question that was before we might have missed. It says, what are the real advantages of IES over Energy Plus? And any comment about Design Builder or Symergy?
Okay, sorry. That was from Alex. Well, I only used Energy Plus once when I was at college. And I think for Energy Plus, I mean, lots of modeling tool, they use Energy Plus as an engine, like Design Builder you mentioned, is actually they use Energy Plus as an engine. So I think Energy Plus, you spend a lot of time developing the model, but you spend more time debugging. That is due to the nature of the Energy Plus, how they develop the software. And it's not user-friendly, I would say. If you have great background in terms of programming and encoding, you probably feel very comfortable of using Energy Plus. But if you don't, I think it's hard. So IES, I would say they offer great. Let's say if you do a lead project, they offer like navigators. They offer pre-built modules for that, and it's great for industrial type of users. I mean, definitely you can use IES for academia purpose, but I would say it has the reason why a lot of industry people like it is because the steps and the workflow. It's great. And also the complexity of IES, you can do a lot of stuff in IES. You can model basically whatever, whatever you're saying, you see on the drawing, whatever system. As long as you understand, you can build approximate. Even you don't have that module, you can build something by yourself. I think that's a great feature for advanced users. Design Builder, I never used Design Builder, so I can't really comment. I used Symergy in the past. I think Symergy is something like eQuest, but I think the flexibility and so Symergy, I don't think you can model very complex HVAC system, and it has limitations in today's application, especially in a big size, like 20-story, 30-story commercial type of building. That's just my personal opinion. I know people have different preference. People use different tool. So that's just my personal experience. All right, next question. How you guys provide financial analysis for particular project? Do you outsource or use some Python R-based programming software? That's probably a question for Benny. Right, Benny, you want to answer that?
Sure, I can answer that. We provide financial analysis for lots of projects. It just depends on what the type of assessment is. If it's a life cycle cost analysis, or if it's simple payback analysis. We do a lot of parametric iterations up front during development and construction to try to help advise people on the best way to put the windows and facade systems together, percent glass, type of glass, reflectivity of the glass, which HVAC systems have certain advantages, to help inform decisions through that way. But as far as using Python or R-based programming software, we haven't had to integrate into that platform. That's usually done when you need to do something that the software is unable to simulate. I think the closest that we've probably done is we've done some integration with transys modeling, where particularly for geothermal and geoexchange type projects, where we need to look at the soil and see what the thermal drift that the geoexchange system will be putting into the ground. Transys is very good at modeling things of that nature, where it can do a 5-year analysis of what the drift will be, and we can then identify what the load will be. So we've integrated that into IES before. The one particular advantage of IES over some of these other softwares is it's got a great custom ability to put in. You can import actual profiles and use those profiles very easily. A lot of software doesn't allow you to make micro time level timescales. So a lot of the measurement and verification work we do, we've had data down to 1 second that we've been able to use some IES platforms to derive better, real powerful schedules for. And then just kind of backing up on the previous question about design builder, design builder like Open Studio or overlays to Energy Plus, they have their advantages. All of those programs are really good at taking things like with SketchUp models and building geometry very nicely. But in general, most of them lack the ability to do logic diagram level HVAC programming, which is extremely important in any modeling software. But having the ability to do something with logic level, which the Python programming, the Transys lets you do in that realm, and IES has quite a bit of capability within that. So that's some of the advantages of those software.
Thank you. All right. Yeah, thank you guys so much for spending time with us, and hope you guys are staying safe and healthy. If you guys have more questions, you can, I have my email here. You can just shoot me an email. I'd be happy to discuss some of the, some of the topics we have, very common in modelers. Yeah, thank you so much. Thank you so much.